Hi guys, welcome to my channel. It's been a long time since I uploaded to the channel, just due to some ups and downs in my life, but now I'm poised and ready to get back on the road. If you are my subscriber, you probably know that this channel is mostly dedicated to C# programming regarding the ETABS plugin. I want to add some new features to the channel, let's say expanding our realm to some useful software like IDEA Statica and advanced Stiff. I promise I will be uploading in regard to C# programming and ETABS plugin as well in near future. But today's video is about a column-based design in IDEA Statica, as you see in your screen. If you are not familiar with IDEA, let's introduce it to you first. It's a software using finite element method to model steel connections. In particular, I found it very useful and very easy to learn. Actually, the most positive feature about the software is that it is quite user-friendly, unlike Abacus. Abacus is useful as well, don't get me wrong about that, but it's not quite user-friendly. Abacus is more suitable for research purposes than design. Okay, let's keep the intro short. You are all probably here for the real deal, not some random dude's rants. First, we will learn the AISC requirements for column-based design. Then I introduce you to an algorithm to design the connection with only your pen and paper using basic math and physics. And then we get to IDEA to model the connection and design it. We will compare the results from the software with what we obtained from those basic maths and physics. Okay, before we get to the work, let's say that the video is divided to different parts and different sections. You can jump to the IDEA Statica part, and you can find the timestamps and different parts in description down below. Well, this is our ETABS model, 5 steel story building. I want to design one of its base column connection. In this specific column, as you can see, a bracing element is also connected to the joint. We shall not go through designing of gasket plate required to convey the axial force of the bracing element, since it is a whole different story, but we will consider its presence on the base plate to get as real as possible. So the effect of both the column and the bracing element should be considered in the designing procedure according to AISC. In order to extract designing forces, we get to the AISC code. They provided us a route to determine designing forces. This is the section you can find specific codes regarding column-based design. Here, in seismic provision for structural design. 3 different forces should be applied to the connection at the same time. First is axial force. Required axial strength should not be considered less than the greater of A and B here. And the second force is shear force. The required shear strength consists of summation of 2 parts, the horizontal component from the required strength of diagonal brace connection and lesser of the following 1 and 2 here. And the third is about flexural moment. The required flexural strength, if the column base is designated as moment connection to the foundation, should not be less than the summation of flexural strength of diagonal brace and lesser of 2, 1 and 2 here. Okay, so get back to the ETABS model. As I said, this is a 5 steel story building specifically modeled for this video. Let's get to the base level here. Okay, this is the base joint that I want to design as a rigid connection. As you can see in the elevation window, there is a diagonal brace also connected to the joint here. In addition to the column itself. So in order to extract the required strength of the connection, we go to the table here and then analysis results, then reactions, and then right click on joint reaction, then click on show tables. So here we should read the maximum axial, shear, and flexural forces created by the load combination with overstrength seismic load. So before you read forces, you should run the analysis based on the overstrength seismic load. It is due to the requirements of AISC. First, we get the maximum axial force. We should get both positive and negative axial forces. Do the same for shear and flexural force. Get the maximum amount in each direction and get the corresponding forces in the perpendicular axis as well. For example, in order to get the axial force of base joint number 5, here give the unique name 5, and then in output case select all the load combinations and then click on apply. Okay, here read the both negative and positive absolute maximum. Well, there is Fz is representative of axial force, so there is, okay, here 291 ton positive force, and here I believe, okay, okay, here there is a 166.52 ton negative force. Just keep in mind that negative axial force indicates that it is a tensile force, and positive axial force indicates that it is a clamping or compression force. As I said earlier, we do the same for shear force and flexible moment as well. Shear forces and flexible moments happens in both directions, so you should write them both. For example, there is here Fx is representative of shear force in x direction, so find the maximum, absolute maximum here. Okay, 23.2 is the maximum shear force in x direction, and simultaneously there is a minus 9.4 pound shear force in y direction. In general, we will have 4 load combinations. Here I put them all in combination mode. PU is a stand for axial force. VUX stands for shear force in x direction. VUY stands for y shear force in y direction. MAUX and MAUY both stand for moment about x-axis and y-axis respectively. So, and just keep in mind that the maximum VAUY happen when the maximum MAUX occur, and also maximum VAUX happen when the maximum MAUY happens. So put the VAUY as I see here, maximum VAUY and maximum MAUX in same load combination. Here as you see, I put the maximum VAUY and maximum MAUX in the same load combination, and the maximum VAUX and maximum MAUY in the same load combination. So it is up to your model. My model is forced me to do so. So you should go through your model and your specific baseplate design. It is not a universal thing. So, and you see about the picture above. It is a pre-designed connection scheme. We assume the dimensions of the baseplate here, stiffeners, and anchors, and then we check them whether they are qualified to stand the designing forces. These are our designing forces, and the first guesses should be based on your experience in designing the column-based connection, and more you practice and study, the more your first guess is accurate, so you go through less iterations. So in this part we calculate the root sum of squares of both shear forces and flexural moment in order to simplify the process. If you want to design your connection by using equilibrium equations and strain equilibrium equations. But in IDEA, you can simply consider both dual axis shear forces and flexural moments because the software is using finite element method to analyze the connections. As you can see, the VUX, VUY, MUX, and MUY are slightly getting bigger in order to consider the effects of dual axis forces. Well, in the next part, we calculate the flexural strength of column and diagonal brace. As you see, the extent of flexural strength of the column are much bigger than analysis of the structure with overstrength seismic load. In this part, we calculate the flexural strength of the bracing element. So according to the AISC seismic provisions, we should consider the lesser of overstrength seismic load and flexural strength, and then add the flexural strength of the bracing connection. We do the same for shear force as well. Here, as well. In here, the shear strength of the column is much bigger than the analysis of the structure due to overstrength seismic load. But likewise, the flexural moment, we should add the horizontal component of the axial strength of the diagonal brace to the ultimate shear designing force. Just keep in mind, if you have dual axis diagonal brace, you have to consider both of them. In the next part, we obtain load combination 1. PU is 291 compression force or 166 tensile force. VUX is the minimum of these two terms. The first term is shear force due to overstrength seismic load plus the horizontal component of axial strength of the brace. And the second term is shear strength of the column plus the horizontal component of axial strength of the brace. And MUX is the minimum of these two terms. The first term is the flexural moment due to overstrength seismic load plus the flexural strength of the bracing connection. The second part is flexural strength of the column plus the flexural strength of the bracing connection. And as I said earlier, we have to put VUY and MUX in same load combinations because it is more likely to have maximum MUX and maximum VUY in same combination. So and then it is not a universal thing. It happened in my case. You should check your connection to determine whether VUY and MUX happen simultaneously in their maximum amount. So in this part, in the next part, we have here we determine material properties, and next we assume the dimensions of the base plate. As I said, in both simple way and finite element method, we have to assume the extent of base plate dimensions and anchorage parameters. So as you see, we assume that the base plate in X direction has 640 centimeters in length, and in Y direction it has 646 centimeters as well in width. So, and in the next part we start the analysis. I don't want to give too much time to this part because you all probably here to see the IDEA Statica part, so you can download the PDF from the link in the description down below and deep dive into it to have more insight about simple procedure to design baseplate. But just a quick review. Okay, in this part we calculate the eccentricity of axial force. Next we determine the E critical here to see whether the base plate is totally under compression force from the concrete foundation. It is quite like an algorithm. You first check eccentricity with ESCR, and then if E is bigger than ESCR, we go through another solution, and even that solution is not valid, we go through another solution which is using strain equilibrium equations. So we have these equations here, and then equilibrium equations here as well. So and after that, after we analyze the base plate according to these equations, we can check the ACI requirements for anchorage to concrete foundation, which is quite long and tricky. But the good news is that the IDEA check this part as well. For example, tensile strength of the anchorage, concrete breakout strength of anchorage and tension. These are all be checked with IDEA as well. So we get back to this part again after we are done with IDEA. So I wanted to see the difference between these simple equations and finite element method in IDEA, and to which extent we can trust the result from simple equations. Well, this is the IDEA Statica software based on finite element method using shell elements to model connection parts. So press on connection. Well, this software has provided so many pre-modeled steel connection, like beam to column, beam to beam connection, and stuff like that. If you can't find your template connection, you go to this part. It gives you a blank 3D space, and with some provided modules you can define the kind of connection you have in your mind. In our case, which is a column-based connection, we get back to this part and then choose a box-shaped column. Then on the right side we have two options. One is provided without stiffness, and the other one is provided with some stiffness. I choose without stiffness because I want to define them manually by myself. And on the right side we choose the grade of steel in use, anchorage diameter, welding grade, concrete strength as F'(C), and design code and approach to design, whether it is a LFD based design or AST. I choose grade A16, A36 as it is now, and 36 3 to 5 M for bolt assembly, E17 70 for weld grade, and I choose 45 psi for concrete grade. It is around 30 megapascal, and the design code is AISC. That, as you can see, I choose US flag, and then in subcode you can choose whether to design whether it is RFD based or ASD. Now click on create project. It takes a few minutes to build up the template. Okay. Okay, if you are a newbie to the software, my advice is that you better follow my every step. Once you are used to the environment, I recommend you to walk through everything you are curious about, and do not forget to check out other creator tutorials as well to expand your knowledge and understanding of the software. Well, there is our connection. First, I change the column here. Click on call, and then click on add new. My column is fabricated from steel plates, so I choose welded compound, and then I choose box shape column. Here we can determine the properties and dimensions of the column. I change the height to 340. Thickness of the upper flange is 20. The width of the upper flange is 340 as well. Bottom flange is similar to the upper flange. I give it the same numbers, and the thickness of the web is also 20, and the inner distance of these two webs, it is around 300. So then click OK. As you see, the column is changed to what we determined earlier. And then after that, go to operation, click on BP1. We can modify our base plate here. My base plate is 64 centimeter in width and 64 centimeter in length. On the offset, you may change the dimensions. Top means the distance of base plate edge from the top edge of the column, so it is 150 millimeter. Likewise, the top, you may change the left. So my column is 340 millimeter long in both directions. It is a square. We added 150 millimeter from each edge of the column, so 340 plus 2 times 150 equals 640 millimeter or 64 centimeter. It's a quick description to why I added 150 here and here. So in the next part, we go to the anchors. You can click on add new here in front of type, then choose 36 A325M. It means that the diameter of anchors is 36 millimeter, and the A325 is representative of the optimum tensile force it can stand. Then click on OK. In the next part, change the length of the anchoring to 700. Next part, we can choose whether it's a straight anchor or headed. I choose washer plate rectangular. And in the next, you can change the size of the headed anchors. I change 100 to 120. And you can see everything you change here happens in real time on the left side here. So in the next part is referring to the configuration of anchors on the base plate. First, I give them both 0 values to show you that the center of the anchors is located exactly on the edge of the column. So I want my anchors to be 60 millimeters far from the edge of the base plate, and I have a 150 millimeter net distance from edge of the column to the edge of the base plate. 150 minus 60 equals 90. So I give both of them 90. But there's a problem. I want more anchors parallel to both axes. So in the left layer part, I write down another number. For example, 50. As you can see, 4 anchors are added to the anchors we have, but I want them to be distributed equally on the edge of the base plate. So I change the sign of the 50 to -50. So the location of these 4 new anchors is changed, and I want them to be distributed equally. So the width of the base plate is 64. I retract 2 times 60 from it because I want to get the net distance between these 2 anchors here, this one and this one. So 64 minus 26 equals 52. Now I divide 52 by 3, and the result is 173. 173, yes. I can change 50 to 173. Now you see the anchors are distributed equally in distance from each other. So for other edge, we have 2 ways, but I recommend you to go to the editor here, click on editor, and click on copy here. So a new hole on the base plate is added. Leave the X value as it is, change 260 to 86. Now number 9 is located as 1 you want it to be. Click copy again, change 86 to -86, and by the way, we divided 173 by 2 to get the suitable distance of the we need to put our holes here. So create another copy. This time change 260 minus 260. Okay, another copy, and change it and the y value to 86. So as you see, we created all anchors and holes in the base plate we need according to pre-designed configuration. We had is the pre-designed configuration. Our goal is to recreate this configuration in IDEA. So then here click OK. Okay, all the holes, all the anchors are added to the template and the connection here. Okay, next part is about welds. You can choose between fillet weld and groove welding. Okay, I choose both flanges and webs to be connected to the base plate with groove welding. And okay, here you can choose the grade of the welding stick. I give it E17 as it is, and this is the thickness of the weld. So for the groove welding, the thickness of the weld is about the thickness of the smaller plate. So it is leave it as it is. So in the next part, we get to the concrete foundation. We can change F prime C here. We'll leave it that part since we assigned it before and it is okay. Then in offset part, you may assign the distance between the edge of the concrete in each direction to the edge of the base plate. If you write just one value, IDEA will assume it for 4 directions. I want the base plate to be 150 millimeter from one edge of the concrete and 3000 millimeter from other edges. So I write 3000, 150, 3000, and then 3000. So okay, you can see the foundation is changed to what we described here. So, and in the next part, we can assign the depth of the concrete block. I change it to 950 millimeter. It has to be slightly bigger than the length of the anchors, and it is up to the code you are using. You have to provide the minimum requirements of concrete to boards and to anchors. So in the next part, we should choose how the shear force is conveyed to the concrete. I choose anchors here. Okay, well, so far so good. It is well done. So far we assigned the column and base plate geometry. We defined anchors and the geometry of the anchors. We defined the dimensions of concrete block. And next we are going to add some stiffeners to the joint. Well, right click on operation, then click on new operation. A new window will pop up with some features you can add to your connection template. I want to add stiffness, so I press on this icon here. A new plate named SP1 is added. You can rename it if you want. Just right click on it and then press on rename here. I leave it that way, so on the right side you can change the material thickness and location of the plate. I change the thickness to 50 millimeter here. Probably you notice no new plate is visible, so go to this part and press transparent. Okay, now you can see the plate in the middle of the base plate and column. I want the stiffener to place like this on base plate. I want this one. So get back to the idea. I change the value of Rx here to 90 degrees. The plate is now 90 degrees rotated about x-axis. Now change the values according its dimension. I want it to be 640 millimeter in width and 300 millimeter in length. Now I have to move it, and then I have to move it to edge of the column. So in this part, I gave it 340 343 and then 300 and this one 0. So it is now I have to move it to the edge of the column. So in this section I change the value to change the value of y to minus 177.5. So it is 340 divided by 2 equals 170 plus the half of the plate thickness. So I obtain 177.5 from this equation. So far so good. Now I want to modify the shape of the plate. Go to the editor, click on chamfer. On the right side, select the corner and then change the value to what extent you want the corner to be cut. So I choose 50. I select corner 2 and then I click on apply. Another chamfer, corner 3 and value is 50. Okay, then I click on apply and then press on OK. So now we have to define welds of the plate to column or base plate. Right click on operation, choose new operation and then press on this icon here, weld or contact. New operation named weld 1 is added. In this particular weld I want to define a line of weld that connects SP1 to column on the right side. On the right side, select edge to surface and then select weld here. In the first plate part, choose SP1. Look at the connection into transferred mode. As you see, edge number 4 is aligned with the web of the column. So choose 4. In the second plate part, choose column web 1. And in welding section, choose fillet weld front side and give the thickness of 7 millimeter to it. So go to solid mode to see whether the weld line is located in right position. As you see, it is a weld line as we intended to be located. So, and now I want to add a welding line to connect the corner of the column to SP1. Now before that, let's connect the SP1 to baseplate. So make a copy of weld 1. Leave the above as it is here. Change the first plate index to 1 and change the second plate to BP. BP1. Okay. And in welding part, choose the side of the fillet welding, the right side of the fillet welding. As you can see, it is in, you can change it to this one. Okay, no. I think this one is okay. So the thickness of the weld is 7 millimeter. Likewise, the weld 1. So now it's good. So now make a new copy of weld 1. Change the first plate to column bottom flange 1. Column bottom flange 1. Index 2. and the second plate to SP1. Adjust the side of the fill welding to the right side. Choose the transparent mode. Okay, you can see here if it is located correctly. Okay, now you see a line of weld is added in the position that we intended to be at. So create a copy of weld 3. Now we should only change the first plate to column top flange 1. I think it's perfect now. Let's check it. Okay. Now, as you see, the weld line is located in the place that we want to be added. Now, all the weld that we wanted to define is now well defined and well located. So now I want to add a similar SP1 to other side of the column. Create a copy of SP1. Go to transparent mode again and change the value of Y to 177.5 millimeters. Now you see the new plate is in the right position. Then we should create all the weld for SP2, likewise the SP1. So create a copy of all 4 welds above and change the parameter as I changed it. Okay, create a copy of weld 1. Change this one to SP2. Column weld 2, okay. Copy of weld 2. Now create a copy of weld 3. Okay, create a copy of weld 4. Okay. All the welds of SP2 is now well added. So, so far so good. Well, after that we are going to add other stiffeners. Add a new plate. Go to transparent mode. If it is needed, change the RX and RY to 90. It is our plate here. The plate should be 135 in width and 300 in length, and change the value of Y to minus 185 to place it in the right spot. So 135. 300 and 0, and change the y value to minus 185. Okay, weld is now located in the right position. Go to the editor, click on chamfer, select the corner 1, and change the value of it to 20. Create another chamfer and select corner 3 and give 50 mm as its value. And then press OK. So create a new weld. On the right side, leave the above as it is. Set first plate to SP3. Index 3. And set the second plate to SP1. And choose double fillet weld with 7 mm thickness. So now get it solid. The weld is added again. So now we need more of SP3, but in different locations. Create a copy of SP3. Okay, just one weld. We forget the weld of SP3 to base plate. So create a weld of weld 9. Change the index of first plate to 1. And set the second plate to base plate. Okay, now the weld is added. So create a new copy of SP3. The value of change the value of X to 173. 173. Okay, all the parameters are the same as SP3 and leave them as it is. Now copy weld number 9 and 10. Copy and create a copy of weld 10 as well. So you only need to change the first plate to SP3 in both weld 11 and 12. And in weld 11 as well, change it to SP4. Okay. Create another copy of SP3, weld 9 and weld 10. Change the value of X in SP5 to minus 173. And select the weld 13. And change the first plate to SP5. And do the same for weld 40. Okay, so good. Now we need to add the stiffness to the other side of the column as well. Create another copy of SP3. Change the value of B1 to 0 and B2 to 135. Change the value of Y to 185. So choose a transparent mode to see. Okay, it is added in the right place. So when we need to change the chamfers about in this plate. So go to the editor. So delete these two chamfers here. Delete. Okay, now add your chamfer. Change the value. Let's change the value to 20. Select the corner 4. Create a new chamfer. Select the corner 2, and the value of it is 50. Okay, then press OK. Okay. So create a copy of weld 9 and 10. And change the first plate to SP6, index 6, and set the second plate to SP2. Okay, go to the solid mode to see whether the weld is located correctly. Okay, good. Then select the weld 15 and change the first plate here to SP6, index 2, and change the SP1 in the second plate to BP1. Okay, now all the weld is added properly. So now make another 2 copies of SP6 and create welds for them as well. So create a copy of SP6, create a copy of weld 15, and create a weld of field 60. Now choose SP7. Change it to SP7. Okay, now create another copy of SP6 and weld 15 and weld 16. Okay. Choose SP8 and choose SP8. Well, all the stiffeners all added. Only we have two the 2 stiffeners are still remain. So well, add new plate to operation. Click on transparent mode if it's needed. Okay. Set the RX value to 90. Change the value of B1 to 150. B2 to 0. H1 to 300. And H2 to 0. Now we need to relocate the plate to its right spot. Change the value of X to minus 170. So as you see, there is a single plate added to the spot here. So now go to the editor, create two chamfers. Select corner 1 and 3. Corner 1 and 3 and set the value to 20 and 50 respectively. Well, perfect. Now we need to add welds, create new welds from new operation. On the right side, leave the above as it is. Set the first plate to SP9, index 3. And set the second plate to call top flange 1 as it is we see now. So, and change the thickness of the weld here to 7 and make sure it's a double fillet weld. So create a copy of weld 21, assign SP9 index to 1, and change the second plate to BP1 because we want to create a weld in order to make connection of SP9 and base plate. So make sure that the size of the thickness of the weld is 7 millimeter and it is a double fillet weld. So perfect. The only thing is remain is the gasket plate and bracing element. For the record, you can model bracing element to connection and assign its forces based on AISC, specifically to the brace, and you can also ignore diagonal brace and add its forces to the node. For example, this is exactly what I've done here to determine the design forces for simple method design. Here I added the corresponding forces of the brace element to the node via VU3 brace, X for the shear force, and also here, for example, MU3 brace is a representative of the flexural strength of the brace, and I added to the flexural strength of the column. So I do the same here in Statica, and I keep it this way in IDEA Statica as well. So create a new plate. Okay, there it is. Okay, on the right side, change the Rx to 90 degree. Then B1 to 0, B2 to 426, H1 to 480, and H2 to 0. Then change the value of X to 170. There it is. It is our gasket plate. We need to create some cut in the corners to make it look like this one here. Okay, so go to the editor, create two below from clicking on this icon here. So set the corner for first bevel to 1 and assign 294 and 198 respectively to A and B. 294, 1, 9. Okay, and now for the second bevel, set the corner to 2. And assign 276 and 186 to A and B. 276 and 186. Okay. And then press OK. Now enjoy your gasket plate to be added to the joint. Now we need to add welds too. Create 2 welds. Okay, click on weld 23, set the first plate to SP10, index 5, SP10, I believe index 6, and set the second plate to column bottom flange. And I want it to be a double fillet weld with thickness of 10. Okay, go to solid mode and check whether it is added correctly. Okay, that's correct. Go to transparent mode again. Now click on weld 24. Assign SP10 as the number for the first plate, and then index, choose the index number 1. For the second plate, choose BP1, but I want it to be a groove weld. Choose groove here. Okay, that's a groove weld here. So keep in mind that these 2 welds should also be controlled when you design gasket plate bracing element as well. It is very important that you designing weld elements when you design the gasket plate specifically for conveying the axial force from bracing element to the column and base plate. So, okay. Well, so far so good. The connection is entirely modeled. Now we get to the loading and imposing designing forces to the node. These are, as I mentioned earlier, these are our forces that should be exerted to the connection at the same time. In load combination 1, we have 291 ton axial compression force here, which is approximately 2850 kilonewton. Okay, get back to IDEA. Under the load effects, click on LE1, and under the N here, N is representative of axial force. Change it to minus 2850. I put minus because in IDEA, compression force should be in negative direction. And we have a VY here. VY is 20.1 ton, which is also VY in our model in IDEA, and about 197 kilonewton. And I put it in such a direction that is more critical. In positive direction, it will cause more chaotic situation, it will cause shear breakout of the concrete alongside the edge of the foundation. So I put it that way. And finally, we have here MUX. MUX is a 52 ton meter, and it is equivalent to MSZ in our model. It is about 510 kilonewton meter, 510, and I change it to minus 510 because it is more detrimental to the connection due to creating tensile force in anchors near the edge of the concrete foundation, which is create a more chaotic situation and it will lead to achieving more conservative design. Okay, so copy LE1, but this time put positive 1626 as the tensile force here, 1626. Tensile force in IDEA should be in positive form. Create another load combination. Create a copy of LE2. This is LE. Okay, put minus 2850 here again because we want to model this one load combination number to VUX and MUY. So VUX is VZ in our model, and it is about 373 kilonewton, and it is not that it doesn't matter that which direction you put it in, because from both sides we have same distance from edge of the concrete, and then we should be assigned MUY. MUY and it should MUY is also MUY in our model, so it is about 30.7 ton, which is actually approximately 137 kilonewton, and change the MSZ to 0 here and VY to 0. So, and then create a copy of LE3, and this time we change the axial force to positive 1626 kilonewton. That's it. Good. This part is also done. The model is finally completed, and we can analyze the connection. Zoom in to see how the forces are modeled in the node. And okay, so two different analysis is needed: the elastic plastic analysis and stiffness analysis. First, we go through elastic plastic analysis, and then we go through the stiffness analysis. Okay.
Well, now click on EPS here. It stands for elastoplastic analysis. ST means stiffness analysis, and we get to this part after we finish EPS analysis. So first click on EPS here, and then come here and click on calculate. It takes a few seconds up to a few minutes to finish the calculation, and it depends on the calculating power of your system. For my system, it takes usually 5 minutes to finish the calculation, so I will pause the video and then I wait the calculation to be finished, and after that I restart the session.
So the analysis is done. Some plates, welds, and apparently all anchors are not qualified. First, we check plates. IDEA Statica use a 5% strain limit to check whether a specific plate is qualified to withstand the forces or not. This is a criteria from EU code, but AISC doesn't have such a criteria, but similarly, AISC define a thing called connection strength. You can find it here in AISC code. Yes, here, connection strength. The strength of a connection is the maximum moment that it is capable of carrying, MA, as shown in figure CB32. This is the picture here. The strength of a connection can be determined on the basis of an ultimate limit state model of the connection or from physical test. If the moment rotation response does not exhibit a peak load, then the strength can be taken as the moment in a rotation of 0.02 radian. There is also an explanation why IDEA use 5% strain limit to pass plates. You can find it here. This is from a website, ideastatica.com. You can find it in this address here. And the whole page is talking about why they use 5% strain limit in accepting plates. And it is talking about the strength connection defined in ISC and compared it with 5% strain limit criteria. It discussed that 0.02 radian rotation of a connection is produced nearly 5% strain in connections plate. So they are kind of similar, okay? And we get back to this after we run the stiffness analysis as well. So get back to the idea and then click on check. Here on the right side, you can see the results of the analysis. As you see, all plates except the base plate has passed the bar, and we should increase thickness for the width or length of the base plate. I recommend you to increase the thickness if you see that anchors do not meet the design criteria. You should be increasing the width and length of the base plate. Plates of the column are also not qualified, as you see. It is not important because column will not be designed with these loads, which are from overstrained seismic load, according to AIC. And also, according to AIC, base plate, stiffeners, welds, anchors should only design with these forces. You can see here in seismic provision for steel structure. Here in column-based section, it is talking about requirements of column-based design. So it is the available strength of steel elements at the column base, including base plates, anchor rods, stiffening plates, and shear log elements shall be in accordance with the specification. So, and the rationale behind it is that we don't want to see failure in joints, so we design them with much higher forces than we design members. Okay, and get back to IDEA Statica. If you click on each plate, you see the maximum tension and strain occurred. For example, here, if you click on, for example, SP10, you can see the diagram of stress strain within the plate. So there is a concentration, stress is concentrated here. So, and also if you go to check anchors, all of them are failed. Click on one of them, for example, A1 here, okay? Click on this icon here. You can see that the design procedure of the anchor A1. Right click on it and then print preview. This is the summary of anchor design. In chapter 17 of ACI, you may find all the requirements needed, and also I provided them in this example here in more detail. I also provided all the requirements you need to go through according to ACI here. For example, tensile strength, concrete breakout strength of anchors and tension, with more detail and with more concentration on little stuff. Okay, so then get back to IDEA again. So this particular anchor for tensile strength is enough to withstand the tensile force. The tensile force, it is NF is the tensile force, and phi NSA is the strength the strength of the anchor in tension. So, and the safety factor is about 1.5, I guess, and which is an indication that we can reduce the diameter of the anchors. But in the next part, concrete breakout in tension, the group of anchors in tension do not pass the bar. In the example I provided, you can see more details. For example, how we measure. For example, we measure ANC and CO. You can see here that we measure them in more detail. ANC. For example, and stuff like that, you can see them in more detail in the PDF file. The link of the download is in description down below. And okay, the next one is concrete. The next one is concrete pull-out resistance. It is enough to withstand the tensile force in the anchor. ABRG here is the area ABRG. Here is the area of the washer we define at the end of the anchor. And in the next part, we check concrete side face blowout resistance. It is also enough, and as you may see, these two parts, concrete side face blowout resistance and concrete pull-out resistance, are dependent on ABRG. ABRG here and here. So in the next part, we get to control the shear. Net area of the anchor is enough to produce suitable resistance. Let's say conquer the shear force. Safety factor is very high here. We may reduce the diameter of the anchor. We can do it. In the next part, the IDEA control the concrete shear breakout. Here, Likewise, the concrete breakout in tension, this one is also failed. And the next one is concrete pry out resistance, which is not failed. So here you can see that it is not failed. So the reason anchors are failed is that the concrete is not capable to withstand breakout in tensile force and shear force. Why is that? Because the base plate is near the edge of the concrete foundation, and you either increase the distance between base plate and edge of the concrete foundation, or you add some reinforcement. The location of the base plate is mostly forced upon you. The only feasible way is to add reinforcement. We get back to this part again, but let's check the welds. As you can here, click on welds. Some of them are passed and some of them are not. For example, here SP10 to bottom flange of column and SP1 to web of the column. Some of them are passed and some of them are not. So the only way to strengthen a weld line is to increase its thickness, but sometimes if you add rigidity to the connection, it may reduce the forces applied on the weld, or you can use weld stick with higher grade. Okay, well, the second analysis was also done. I increased the thickness of some plates and some welds. All of the welds are in safe zone, and all of the plates are also in safe zone, except this one is SP10. If we go to check and then click on plate, okay, as you see, then find SP10 and then click on it. As you see, only a very small portion of the plate have passed the criteria of 5% strain limit, but most of the plate is under that limit. Most of the designers ignore this small portion because it is mostly due to concentration of stress, and sometimes it is due to the error in final element method as well. So we can ignore this part because most of the designers do that. But if you want to achieve a very pure plate, you can increase the thickness of the plate, or maybe the length or width of the plate to achieve what satisfies you. So, and then click on anchors here. As you see, all of the anchors are failed, and I showed you before, this is not related to the diameter of the anchors. As much as you increase the diameter, you will see no change. In our case, we need to add reinforcement to pass the requirements of concrete breakout in tensile and shear force. Here in our file, I provided a procedure to check ACI requirements in order to withstand concrete breakout in tensile and shear force. Here is concrete breakout, strength of anchors in tension. In order to design reinforcement, we should acquire NCBG. And if you want to check it for yourself, you have to go through this procedure here. And you need to acquire summation of tensile force in anchors. In simple equations that I show you before, summation of tensile force in anchors according to simple procedure is 185 ton. it is approximately 850 kilonewton. But in IDEA, you have to click on one of the anchors in tension. Click on print preview. Go to check the breakout resistance of anchor in tension. Then find NFG. This NFG is here, and you can see that it is 2178 kilonewton. It is bigger than what we acquire from superinclusion in this fab. So it is more conservative than what we obtained from our simple math and physics procedure. So get back to IDEA again. Okay, you need to have this number, and then back to this file. Here, here in this part you have to put NFG equal to VAS, and then assume the diameter of reinforcement you want to use, A'S, and solve the equation to find NV. NV is the number of reinforcement, and A'S is the area of one bar as a reinforcement. So I use V30, 30 millimeter as a single bar, and then we calculate NV. And NV is 4.25, and we can use, for example, 5 of the V30. But keep in mind that you have to use NFG here as T or VAS. So, and in concrete breakout and shear, likewise the concrete breakout and tension acquired both VG and VCBG. If we find, okay, here VCBG, and here you can see that VG, that we assume it as here as VU. So get back to IDEA, go to the part for breakout and shear. Yes, this one. VG is 197, and here we calculated VG as I believe VG here is VUX. Okay, it is IDEA has calculated for 197 kilometers. So, and here you can calculate VAS, put VG here as VUX. Here is safety factor minus VCBG. VCBG is also can be acquired here. VCBG here, and then you need to assume VAS and then find NV. NV is the number of reinforced bars, and also keep in mind that these reinforcements have a pattern to be located in the under the base plate. If you go to ACI requirements, this is how you should put the reinforcement to withstand axial force. in concrete breakout in tensile force, you should be put them in this situation and in this pattern. But for withstand the shear force, you have to put the reinforcement in this pattern here to withstand the concrete breakout in shear force. And you can find both of them in ACI requirements for shear and tensile force in chapter 17 according to concrete. So okay, that's okay. I think that was important to show you that if you need reinforcement, IDEA doesn't provide you a procedure to calculate needed reinforcement, so you have to do it by yourself. And this is how we have done it here. For example, to this formula here for shear, and here, okay, here, and this one is for axial force. So far so good. Now I think we have to go through stiffness analysis to find out whether the connection is rigid, semi-rigid, or pinned. Create a copy of the current project. Here, click on copy. Okay, as you see, we have CON2 and choose ST here. So now go to ETABS. Okay, ST is chosen. So now go to ETABS. Okay, in this part, create an envelope of all your load combinations and run the analysis, but this time without overstrain seismic load. It is very important that you should do it without overstrain seismic load. And if you go to the table, then analysis result, reaction, and then join to reactions, then click on show table. In unique name, we have to choose 5. In outputs case, we choose envelope ENV as representative of envelope of all load combinations. Okay, as you see, we have 2 load combinations here, max and min, and you have to put both of them in IDEA Statica. And okay, get back to IDEA in design. In under the load effect, choose LE1. Come back to here and see if FZ is representative of axial force. 1875. 1875. It is a compression force because as I said before, in ETABS compression force is positive, but in IDEA Statica compression force you have to be in negative pattern. So, and then V by 97.12. 97.12 . 97.12. Vx is Vz, 130. And MX is torsion, if we don't put it here. And Y is the moment about Y-axis. Oh, sorry, here, MZ. In ETABS, MZ is representative of torsion. So MX is kilonewton millimeter. Before that, okay, let's change the, okay. Okay, mx is rotation about moment in about x-axis. It's 280 kilonewton meter. Here we have to put it as mz 280. You can zoom in to see whether we put them in right direction. So, and MY is MY here, 23 kilonewton meter. 23 point, I believe, 0.8. Yes, 0.8. Okay, so far so good. And go to LE2. Here in LE2 we have minus 644 kilonewton as tensile force. 644. EY is minus 88.8. Minus 88.8. Vx is minus 83.8. Minus 83.8. 0. Moment about y-axis is about minus 25.7, I believe. Minus 25.7. 25.7 kilonewton meter, and this one is minus rotation about x-axis, minus 226.1 kilonewton meter. Okay, and we don't need LE3 and LE4, so delete them. Okay, so far so good. And okay, and then go to column. It is a very important thing that I should share it with you. Click on column here and scroll down until you see the theoretical length for MY and MZ. My column is 3.2 meter long in first story. This is very important to consider This is very important in considering the connection as rigid, semi-rigid, or pinned. Here I ship point 3.2 and 3.2. So if we go to AISC seismic provision, I show you why it is important. I think in AISC, okay, here we have, as you see here in the graph, this is in AISC, excuse me, yes, it is in AISC. As you see here in this graph, if the diagram of moment rotation lays upper this area, here I believe, this area, then it is a rigid connection, and if it lays below this area, it is a pin connection. Anywhere between this line and this line, KS and KS here, it is a semi-rigid connection. This diagram is in x-axis, in horizontal axis is representative of rotation, and in vertical axis it is a representative of moment. So in order to determine these lines, we need to calculate EI divided by L. As you see here, this line is 20 EI divided by L, and this line is 2 multiply EI divided by L. And the software calculate E and I based on material and geometry of the column, but we assign L to this input here in IDEA. Theoretical length for MY and theoretical length for MZ. So it is very important that you put them in correct order. And then press on calculate and wait until the analysis is done. It may take a few seconds up to a few minutes depending on your computing power. Well, okay, the stiffness analysis is also done. Now go to report and click on report. It takes a few seconds to generate the report. Okay, now the report is generated. Scroll down to see the graph here. This graph is the same graph as you saw here in AIC, moment against rotation. So get back to IDEA. And in this table, you can see SJP, SJR. These two terms are very important to define whether a connection is rigid, pinned, or semi-rigid. SJP is 2EIL. SJR is 20 EI divided by L, as you saw here in IC requirements here in this picture here. So get back to IDEA again. And for load combination 1, as you see, the connection is rigid about the y-axis. For load combination 2, the connection is also rigid about y-axis. And for load combination 1, the rotation is rigid about z-axis, but in load combination 2, when we have tensile force, the connection is become semi-rigid. And the total rotation of the connection is below 20 megaradian, and the limit introduced by AISC, as you see here, and also MCRD here. MCRD, as you can see here in the graph, is the ultimate moment you can apply here. Is the moment ultimate moment you can apply to the connection alone. And MJRD here is the ultimate moment you can apply in this specific load combinations. Okay, in order to deviate SJ initial here, and the initial stiffness of the connection, we multiply MJRD by 2/3. Then we draw a horizontal line from the vertical axis at the limit of 2/3 MJRD to meet the diagram, and then we draw a vertical line from the intersection point here to read the rotation on horizontal axis here, on horizontal axis. Then we divided 2/3 MJRD by the rotation we already read from the diagram. The result would be your SJ initial. If SJ initial is bigger than SJR, then the connection is rigid. SJS is the second rotation stiffness. Draw a line between MED on the diagram and 0 point, and then calculate tangent A. So find MED on the diagram, then draw a line from 0.00 here to MJ to MED on the diagram, and then calculate the tangent A. And A is the angle between the line and the horizontal axis. So tangent A is SJS. You can see here, if I show you here, chi I, chi S. Chi I is the SJ initial in IDEA, and chi S is SJS. So in this diagram, you probably understand the difference between SJS and SJS. SJ and SS very better. So the job is done here now. I believe I want to compare the result from simple equations and IDEA. If we go back to the file that we produced to go to simple equations, the total tensile force is estimated less than what we obtained from IDEA. For example, here we obtained total 185 ton in tensile force in anchors, but in IDEA, as you see, as I showed you before, the tensile force in anchors are much bigger. And then the other difference, for example, is the number of anchors in tension. We assumed, for example, here all of them in tension, but IDEA calculated different, so it has an impact to calculate ANC, and so we have different numbers for ANC. And then we found that 20 millimeter as a thickness of the base plate is enough through simple equations here, but in IDEA it wasn't enough, so we increased it to 30 millimeter to meet the 5% strain limit criteria. So it is for example, it is a 30% difference. So, and also some welds here are not qualified and they did not meet the requirements of AISC, but in IDEA, we figured out that it is not enough. But through simple equations here, simple math and physics, it is enough. So IDEA led to more conservative design. If let's say that more accurate than conservative, because IDEA used finite element method, but we used stress equilibrium equations and strain equilibrium equations. But finite element method is a very much more defined and accurate approach to design base plate. So that's it. In the end, I hope you enjoyed today's tutorial. I tried my best to come up with something useful. It took me a lot of times. In general, creating content on YouTube is astronomically time consuming. But I'm satisfied with the result because I pretty covered everything that I had in my mind. And another IDEA tutorial are coming. If you find today's lesson useful, make sure to hit subscribe and hit the like button. And if you want, please leave me a comment. And do not forget to put up a smile and keep yourself educated. Goodbye. See you soon.